Good afternoon, and thank you for choosing this session on confidential computing. It's a technical topic. It can become very technical very quickly, but it's an introduction today, and I try to make it as simple as possible to give you some concepts about confidential computing. So we look at different techniques related to that. But before I start, I just wanted to say a few words about SMILES, my employer. Back in 1939, the transition was about mechanographic systems, and we helped all our customers in Belgium, the social security sector, do this transition. And we continue this mission today with more modern technology, obviously, by bringing know-how, expertise, staff as well, and we also help our customers with bespoke application as well as running their infrastructure by designing and operating their data centers. And for the last 16 years, SMILES has been one of the top employers in Belgium. So if you're interested by a job of architect, analyst, developers, and many others with a purpose, you're welcome to visit the booth at the entrance. So that's enough for the publicity. I'm going to move to the topic of the day, and we're going to look at different techniques for confidential computing. So we talked about homomorphic encryption, secure multi-party computation, and trusted execution environments. After that, we'll compare these different techniques and look at what the market has on offer. But before I start, let's look at what happens if you want to do some computation on encrypted data on your laptop, for instance. So typically, nowadays, the data on our laptops is encrypted on the hard drive, which is good, because if you lose your laptop or if it's stolen, then the bad guys don't get the data. But when you want to process this data, do something useful with it, at some point you need to decrypt it. So typically, what happens in a very simplified way, the data is loaded from the disk into memory, and the processor decrypts the data. Then you have the data which is in clear in the memory, so the processor can do some useful operation on that data. And when this is complete, we encrypt back again the data and store it on the hard drive. So far, so good. Very simple overview of what happened on our computers today. However, we don't work quite like that anymore, and we tend to use our computers as sort of a remote control towards remote systems, remote infrastructure. So here, our data is still encrypted at rest on our computer. It's encrypted when we transmit it over the network, and it's also encrypted on the storage area in the remote infrastructure. However, when we want to process that data and do something useful with it, then we need to do something similar as what I showed on the previous slide. At some point, this data needs to be decrypted. And then comes the question, where are the keys? What happened if someone could get access to that data in the clear, in the memory of these remote computers that you do not control? And so this brings some concerns related to privacy, related to confidentiality, and the sovereignty of your data. Even more so if the data center that you're using, the infrastructure that you're using is not in Belgium or not in Europe, and probably subject to some laws which you don't fully agree with. So that's where confidential computing could potentially help you in trying to address these concerns. And you can imagine that the customers of the employees I talked about, of SMILES I talked about earlier, are very concerned about the protection of the sensitive data. We work in the social security sector. We have to handle a lot of sensitive data, and this is a reason why we started to look at this sort of technology to help us, because some of our customers are considering using public infrastructures for their processing. Right, so the main aim now is to try to move the infrastructure provider as much as possible outside of the trust boundary. And we're going to look at three techniques. So as I said, homomorphic encryption, which allows you to do the processing, the computation directly on the encrypted data. secure multi-party computation, which basically splits the data you want to process in different pieces and send them to different parties for computation. And the last one, where I'll spend a little bit more time, are trusted execution environments, which are sort of secure enclave in which the computing happens. So let's look at each of them in turn with a little bit more detail. So homomorphic encryption first. As I said, the idea is to do the computation directly on encrypted data. So the model here is quite similar. We have encrypted data on the client side, and this is encrypted using a very special kind of encryption algorithm called homomorphic encryption algorithm. And we can send that encrypted data to the remote infrastructure together with a function that we want to evaluate on the data. So we then are in a state where encrypted data is stored on the remote infrastructure, and the remote infrastructure is about to do some computation on that. And to do that, they apply some very specific schema, which will, in fact, apply the function f in a modified way directly on the encrypted data. So at no point does the remote infrastructure has access to the data in the clear. And when the computation on that encrypted data is complete, the output of that particular computation on the remote data center turns out to be the output that we would like, but already encrypted. So it's sent back to the client, and the client can use their decryption key to get access to the final results. Now, there are different types of function that we could apply for that computation, and based on the complexity of this function, we talk about different types of homomorphic encryption. So partial homomorphic encryption, we can do a series of additions and subtraction on the data. Fully homomorphic encryption, in addition, we can do multiplication and division on the data. And in between, with somewhat homomorphic encryption, we can do a limited number of multiplication and additions, multiplication and divisions in addition to the addition subtraction. Now, this might seem a bit obscure, so let's have a look at a concrete example that we can do with our head. So it's very simple, but it will give you a feel of what happened with homomorphic encryption. So our client has two inputs, 7 and 3, and they want to add them. The homomorphic encryption function I've chosen here for that very simple example is simply a multiplication. So the data, the message M, is simply multiplied by the key K. And I'm going to choose K to be 15 in that example. So 7 times 15 is 105, 3 times 15 is 45. 105 and 45 is our encrypted data, which we send over to the remote infrastructure. And therefore, that infrastructure has no idea about the data in the clear. Later, we ask the infrastructure, please add the data together. And the infrastructure is going to apply some function to that encrypted data. Now, it turns out in this very simple example that the operation that we do on the data in the clear, the additions, is exactly the same as we need to do in the encrypted domain. But it's usually not the case. And so, for instance, in the rather popular Paye crypto system, what happens is that in the clear, you apply addition and subtraction, but in a space of encrypted messages, it's converted into multiplications, for instance. Anyway, so in that example here, addition remains addition when we move from in the clear to encrypted. So 105 plus 45, 150, that's our encrypted result, sent back to the client. And for decryption, we just do the division by the key in that case, which is the inverse of our encryption function, and we end up with the result 10. Voila. So that gives you an idea of what happened. Of course, it's much more complex with homomorphic encryption crypto systems. But the key point here is that at no point the data is in the clear in the remote infrastructure. Now, in terms of advantages and cons for that sort of technology, well, obviously, you can compute directly on the encrypted data, which is a key advantage. And so the security also is based on strong mathematical evidence under well-understood assumptions. Many of the math behind that is very similar to other other crypto systems that we use on a daily basis for electronic commerce, for instance. You do not need special hardware, so you can do this sort of computation directly on a laptop like this one. And some schemes have the good idea to be robust to quantum computing, post-quantum attacks. And I think one last advantage, I would say, is that it's an active area of research, and therefore there's new schemes coming more performant regularly. However, there's a number of issues with this sort of techniques. First, if you want to adapt your existing application or create a new one for that matter, you will need the help of an expert cryptographer to help you build the relevant protocols needed to take into account that sort of technology. Furthermore, the existing schema for homomorphic encryption typically do not guarantee the computation which is applied on that remote infrastructure. So if you recall the example I've given earlier, we did an addition on the remote infrastructure, but it could have been a subtraction. And as a client, I have no way to know whether it's been done or not. Therefore, you need to add some additional protocols to verify that the computation which was carried out is correct. And lastly, quite a lot of overhead in terms of engineering. There are some complex parameterization to be applied before you can use these algorithms, and some substantial changes to be made to your application, which make it quite costly. Furthermore, these encryption schemas tend to blow up the data size. So, for instance, some algorithm will turn 1 bit of information in the clear into 4,096 bits in the encrypted domain. So that's multiplied by 4,000 the size of the data. Of course, this depends on the size of the key. But of course, this has some strong impact on the storage as well as on the bandwidth that you need to exchange data. And related to that is the performance of this system, which are not as efficient as a standard cryptographic algorithm, but they do have some nice properties. So that's it for homomorphic encryption. Let's look at secure multi-party computation, which is a different type of confidential computing technique. And let's start with a problem which is inspired by, or a variant of the problem which inspired this sort of technology. So suppose you have 3 large companies who wants to compare their carbon footprint without revealing the value of this carbon footprint to the other companies. So what can they do? One way is to use a trusted party and then give this value to the trusted party, and the trusted party then give the name of that company which has the lowest carbon footprint. Another way, as you can guess, is to use multi-party computation. And I should have said, sorry, that with trusted party, it's always difficult to find one, and you're never far away from corruption. So multi-party computation enables these mutually distrusting parties to compute something on input data without revealing the data to the other party. A little bit more formally, if you have n parties, P1 to Pn, each with an input data of xi, you want to evaluate a function f on these xi in such a way that only the output of the computation, so z here, which is a function of the xi, is learned by the party, and nothing else about the xi value is learned by any of the party. So the data remains confidential. One solution to do that is to first break the function that you want to evaluate on these input in a series of additions and multiplications, and then follow a protocol like this. So each party first splits the data into different pieces, applies locally the function that needs to be computed with a rather complex protocol. And then when the partial results are computed by each of the participants to the computation, they share again the partial results to end up with the final result of the computation. So let's have a look at an example here. 3 parties, P1, P2, P3. Their input is shown here. So P1 has 7. And they want to compute the addition of these 3 numbers here. First step, I said, split the data. So we split the data here in 3 parts in such a way that the sum of each piece corresponds to the input. So for P1, 2 plus 1 plus 4 is 7. Same for the 2 others. Okay. Next step, share the pieces with the others. So that's what happened here. Each party share 1 piece of the data with another party. So in this state here now, each party has a piece of data from each of the other party. And the next step is to do the local computation. So all we're going to do here is compute the sum of the pieces that we received. I should have said we want to compute the sum of the input values. And so P1 computes 2 plus 1 equals 3 plus 3 equals 6, and so on and so forth for the 2 others. Right? So now we have 3 partial computation results. And the last step is to share back this partial computation with each party. So that's what we see here. And the very final step is for each party to compute the final result. So P1, for instance, is going to add 6 plus 3, 9, plus 12, 21, which corresponds to what we wanted initially, which was 7 plus 4, 11 plus 10, 21. So that gives you a feel of a multi-party computation process. Now, in real life, it's much more complicated than that because some of the parties may not be trusted and could badly behave. So the real algorithms are much more complex to take into account the fact that some parties misbehave. But at least it gives you a feel here again of what happens. A different way to look at it, and which is closer to the model I showed at the beginning with the client remote server. Oh, I forgot that step here. Yeah, but I said it verbally. So it's for the client to split the data into pieces and send that to different public infrastructures. So that's what happened here. Each piece is sent to a different remote service, and then the services go into that protocol I mentioned earlier to compute partial results, which are shared back with the client, who can compute the final result by recombining the partial results. As you can see from this example, there's an issue with this sort of protocol because it requires a lot of computation, exchange of data. And that's one of the issues which I highlight here. But the main advantage, of course, is to enable collaboration between distrusting parties. These protocols have been built for that in mind. Also with the fact that you don't need a trusted party to do that. You can agree among that community of participants on some computation protocol to compute securely on the data without having to reveal the input data. Just like for homomorphic encryption, the security is based on well-understood cryptography. And so it's quite strong security here. Again, you do not need a specific hardware to do this kind of computation. You can do it on normal machines. And again, very active area of research, especially in Belgium and especially at KU Leuven, where there's a lot of work being done on that topic. Now, as mentioned, the complexity of that methods make it difficult to verify formally the security, which can be a disadvantage. And in addition, this complexity means that the setup for in your system, if you want to start using it, is rather complex, which means also rewriting a lot of your application to embed libraries needed for multi-party computation. But I think that the main issue also is about the high communication required between each of the participants. We've seen sending the shares of the input data, but also sending back the partial computation, and there's also, depending on the computation you want to do, some additional message exchange between the parties required. And the example I've shown earlier is just for one addition. And I think in most of your application, you do a little bit more than that. So that's for MPC. And now we're going to look at trusted execution environment. Now we're going into the hardware side of things. And the goal here is to try to protect software processes from each other by creating a better isolated environment, and this isolation being enforced by the hardware. And it's not just protecting applications from each other, but it's also protecting the applications from the operating system, from the hypervisor. So from application with higher privileges. And the rationale here is to use the hardware because you cannot have a secure system if the lowest level of your system are not secure themselves. Hence, this additional protection provided by the hardware. There's a lot of work done in this area. There's in particular the Confidential Computing Consortium, which exists and which is trying to standardize this sort of environment. So you have companies like Google, Microsoft, Intel, AMD, and several others which are part of that consortium. Notably, Amazon is not part of it. In terms of requirement, they can be summarized this way. So first, you need a root of trust in the hardware, a root of trust which can hold secrets, which can later be used for instance, for establishing cryptographic keys for authenticating your hardware. In addition to that, you want your memory to be protected by the hardware itself and also encrypted by the hardware. So each application or each virtual machine is allocated an area of physical memory which is reserved by the hardware and encrypted by the hardware. Furthermore, all input-output to your trusted execution environment should be encrypted. So the data in the clear is only inside that protected zone. And last but not least, you want some evidence that the hardware you're talking to is genuine. And so you want some evidence of the authenticity and the integrity of your system. If we look at a very simplified view of a computer here. So that's a host machine somewhere in a data center. The top part corresponds to the software stack with 2 virtual machines. And underneath, you have the hypervisor. On the below part, you have all the hardware part for running all that. Now, typically nowadays, with or at least without trusted execution environment, all this corresponds to some attack surface that could potentially be used by bad guys. Whether they have, so some of them will need access to the hardware, others can do that just with software, but potentially everything can be attacked. And the goal of these trusted execution environment is to reduce to the most possible, this attack surface by reducing the size of the code running in the environment and also by reducing the number of components. And so to end up in a situation like this one, where part of your application, which has to process sensitive data, is protected by a secure chip, which can be one chip on its own or part of a processor. So that if someone has hardware access to some limited extent or has compromised the operating system or the hypervisor, they shouldn't be able to access your sensitive data. Now, suppose that you have such a host machine on this data center somewhere how do you make sure that you're talking to the right machine? And that's one important issue that needs to be solved before you can use this sort of thing. So there's two techniques to ensure that this happens. In fact, if you go to your favorite store to buy a new laptop, you come back home, you turn it on, you see your favorite operating system, you start using it. It's a trusted store, trusted OS probably, so you don't ask yourself many questions. But if you buy a laptop from someone second-hand, you bring it back home, you turn it on, it looks the same, but what happened there? I mean, what's in the software stack? Have application been installed? Could there be some keylogger? You don't know. So what people do usually is they just wipe the hard drive, reinstall an operating system. It's a bit similar here. You offered this machine over there. You don't know much. So there's two techniques to ensure that you are talking to the right type of machine. First, you need secure boot. And that secure boot basically allows to establish some trust from the hardware root of trust at the time the machine is powered on to a secure state. And it goes step by step, first loading some first piece of firmware. And so you're going to check that this firmware, for instance, through some cryptographic hash, correspond to what you expect. And then you're going to load the next piece of firmware, and then you're going to switch to the BIOS and to the OS, etc. And so all that chain here allows you to have a chain of trust to make sure that when the machine is running after power on, it is in a secure state. That's all well good, but how do you know that? It's still this remote machine. So in addition to that, you need another mechanism called attestation. And this attestation is signed evidence that the machine is indeed in this specific state. So for that the application runs on some expected hardware, and that your application, the binary which is executed, does correspond to the binary of your application, modulo some libraries. And let's look at a little bit more details about this attestation mechanism here. So typically you have your local trusted environment where you build your code. That's what you see on your left here. And you start with your code, you generally apply some compiler which give you some kind of binary which you really want to deploy on the remote data center. And that binary is sent to this trusted execution environment which is running and operated by this remote infrastructure which you do not fully trust. So before really using the application that you have deployed, you first want to ensure that the application is your application, the application you expect, and that it's running on the proper hardware. So you're going to ask your application, please send me an attestation. The application in turn will ask the management software which is running on that infrastructure to build the attestation. And the attestation is essentially made of a measurement of what's inside this trusted execution environment. So let's say a cryptographic hash of what's inside. So it's a hash of a memory zone in hardware. So that's one thing, the measurement which allows to confirm we're talking about the right type of application. And secondly, a signature on that measurement. And in signed by, and that's the big question, by whom? Well, ideally by the processor manufacturer, by the manufacturer of this trusted execution environment. So on your side, you receive this signed attestation. So first you verify the signature by going back up the certification chain to a root certificate that you trust. So it could be the certificate of Intel or of AMD. And then you want to verify that the measurement provided in the attestation does correspond to the measurement that you can compute yourself locally. So there's a number of question marks here. Can you actually compute that measurement locally? What if there's a number of additional libraries which are required and you don't have the source code for that? So these are potential issues to consider. Anyway, another nice feature of this attestation is that the application, when it requests initially the attestation, can also include its public key in it. And so when you receive the attestation as a client, you have the public key of the application, and you know you can also establish some strong cryptographic communication between the two. Advantage of this sort of techniques, well, it's based on hardware, and you hope that by trusting the hardware manufacturer instead of the infrastructure provider, you can sort of dilute your or put your eggs in different baskets, so to speak. So you don't have to fully trust anymore this infrastructure provider. You now have another root of trust, which is the hardware manufacturer. Today, this sort of technique is available from the main vendors, and I'll say a few words about that later. And with different ways of implementing it, and it's relatively simple compared to the two other techniques I mentioned earlier, homomorphic encryption and multi-party computation, to use and deploy, whether it's using containers or using virtual machines. The downside, of course, is that you need some specific hardware. So if you want to use that on your own data center, you need to buy the hardware. So you'll have probably to use some other infrastructure provided by the main providers. It's not because it's hardware that is fully secure. You always have some possible attacks on the hardware. Recent timing attacks were revealed recently by ETH Zurich on existing processors, which I'm going to talk about in a minute. But it does add some level of security. Something to also keep in mind is that because now we're using specific hardware for specific features, there's also some potential for being locked up with a specific hardware. Now, infrastructure provider can provide an abstraction layer to avoid that, but this comes as other costs, and in fact, you could have be locked with the particular infrastructure provider as well. And the most worrying for me is that it may be impossible, in fact, to verify the attestation fully independently from the infrastructure provider, and therefore breaking that initial goal of being able to do secure computation on that untrusted remote system. So how do we compare these three technologies I've talked about? There was a nice report produced last year by for the United Nations by a number of experts, and they compared the maturity of these different technologies on different criteria. On the x-axis, you have the level of maturity, and the more you go to the right, the more mature it is. The y-axis, I'm not sure what it is. I don't think I've understood. It doesn't matter for the purpose of that graph anyway. The key point I want to show you here is that for all criteria, the trusted execution environment are, according to that bunch of experts, more mature than the two other techniques, except for one point, which is the soundness of the theory behind the technology. So the two which come first here are homomorphic encryption and then multi-party computation, because we do have a very strong understanding of what's going on behind. While for trusted execution environment, this is reliance on the hardware. And as I said, it's always possible to break the hardware. But anyway, if you want to use confidential computing today, your best bet is probably trusted execution environment, or you wait for the two other technologies to be more mature to start using, or you scratch your head for a long time and you'll be able to use them. Up to you, depend on the funding that you have. Now, let's move on to some hardware examples. And look at what's provided by the main manufacturers. And here, for this sort of computation, there are only two main manufacturers, which are AMD and Intel. ARM and others do not really look at this sort of data centers yet, so I'm just going to talk about these two here. And two different approach. Intel SGX, so Intel Secure Guard extensions, was the first type of techniques which was proposed by Intel. And the idea here is to offer some some techniques to create an enclave for part of or all of your application. So the first thing that you need to do, it's a bit like having some libraries that will be dedicated a certain part of the memory for executing. So you need to declare these libraries up front, and when your normal application is running and need to do some computation on sensitive data at some point, and therefore call this special library, then you issue a special processor call to create an enclave which will be populated with this special library. Computation happens in a way that this library is reserved some specific memory, and it's encrypted. And it's all protected by the Intel technology. And then it goes back to the normal running of the application with the result of the computation. Obviously, this means that you need to rewrite your application to be able to use that and identify which part of your application does need to access sensitive data. You can, of course, run all the application like that, but of course you have a bigger surface attack. Different approach is the a technique from AMD, the secured encrypted virtualization and the secure nested paging, and the Intel TDX, so for trust domain extensions. And there, the protection is offered for entire virtual machines. Each virtual machine is issued a unique key specific to that virtual machine. And the memory allocated for that virtual machine, which contains your application, the operating system, is encrypted with that unique key, which means that the hypervisor, device drivers, and layers underneath, in theory, don't have access to your data. It's protected by this encryption mechanism. And also, of course, other virtual machines cannot access your data. For all type of technologies here, AMD and Intel do provide also some attestation mechanism which allow you to, as I mentioned earlier, verify that you're running on some genuine AMD or Intel hardware and with this sort of properties. I think that's all I wanted to say about the hardware, and now we're going to move on to some conclusions and some recommendation. I maybe was a bit optimistic about the timing. Anyway, so I didn't mention a lot the infrastructure provider. I'm just going to do this now briefly. I had kept out some other slides related to them. I was not sure about the time, but anyway, I'll say a few words about them. But first, some general remarks about the techniques that we looked at. Homomorphic encryption and multi-party computation don't seem to be mature enough today for justifying a use, at least if you're cautious. They have been used in some niche application. Multi-party computation, for instance, was used in Estonia between the Ministry of Finance and the Ministry of Education for doing a large-scale experiment and for doing some extensive statistical analysis on their data. So very sensitive tax data and data about students in the country and jobs, etc. And they were able to do that computation on the combined data set without having to share the data with each other. So that was a very nice example, but that's one of the very few using multi-party computation. On the other hand, as mentioned, trusted execution environments are now deployed by main providers of infrastructures, and they offer better security thanks to, as we've seen, better process isolation with the hardware, memory encryption with the hardware, secure boot, and the attestation mechanism. Now, these infrastructure providers have different offers. When I looked at that last year, it turned out that Azure from Microsoft had the most varied solution. They offer their solution based on AMD and Intel. And so you have a different type of protection offered. So I've seen earlier on the diagram, you can use secure enclave for protecting part of your application. You can use secured containers, or you can use entirely secured VMs based on the underlying hardware technique that you use. AWS offers something which is very different in nature. As I mentioned earlier, AWS is not part of this confidential computing consortium. However, they claim to offer confidential computing technique, and that's part of their Nitro architecture. So Nitro architecture is now available in all AWS data centers, and it's a re-architecture of their data center, which they have done over the last few years, whereby they have tried to remove as much as most of the code which was running on the host computers and putting that into dedicated hardware cards, PCI cards on the host. So you don't have device drivers, you don't have much of the hypervisor anymore, you don't have all that control plane software running on the host. Rather, it's on dedicated PCI cards on the host. And so you have a clear separation here. According to AWS. They do offer also, since April last year, the ability to use the AMD technology, but that's on a limited set of data centers. Google, however, when I looked at that last year, the offer appeared much less mature and diversified than the others, but this may have changed quite a lot. At the time, they were offering solutions based on the AMD technology. Now, for all of them, I think there's an unresolved trust issue, is that the client still needs to trust fully the infrastructure provider in practice. So either the signature of the attestation is a signature from the infrastructure provider, or what's signed as part of this attestation includes a number of software library which are proprietary of the infrastructure provider, and they don't provide yet the source code for that. So you have this attestation about something running, but you don't really know what. Yes, there's your application, but there's a lot of other stuff. And there's a big question mark also about the overall performance impact on your deployed application due to the added complexity of using this sort of technologies. My recommendations would be first to insist of having the ability to verify the attestation independently from the infrastructure provider, so ideally signed by the hardware manufacturer. Related to that, more transparency, and therefore know what's actually signed, what's part of what's running in that trusted execution environment, what's part of the trusted computing base. So you want to know all the software, have the source code for all the software that is running there. Even if you don't look at it, the fact that it's published often help increase transparency and therefore trust in these infrastructures. In terms of key management, you should have at least the ability to import your own keys in that remote infrastructure. Better if you can use your own hardware locally, but at the cost, of course, of latency. If you want to start using any of the three technologies I talked about, the first thing that you need to do is to provide training to your analysts, your architects, and your developer, because this is rather complex and this needs a lot of planning and testing before you can actually start using it in production. And last but not least, keep a holistic view about the security of the system. It's not because you have secured this little bit of computation on the system that you sort it. Data leak could happen on the application side as well, on your client side. I think that's all I wanted to say today about confidential computing. So thanks very much for your time. I hope it was not too quick. And if any of you have any questions, I'm happy to take them. Thank you. No question. Was very clear then. Good. Thank you.